Welcome to This Explainer. I'm really thrilled you're here, because today we are going to enthusiastically break down the physics, the aerodynamics, and the absolutely mind-blowing engineering that makes the B-2 stealth bomber possible. We're looking at a machine that represents a total revolution in aviation, really the ultimate culmination of aeronautics, stealth technology, and tactical design.
For its entire service life, no enemy has ever detected, targeted, or engaged this aircraft. Just think about that for a second. We're talking about a massive flying machine that can completely vanish from enemy radar networks, deliver incredibly precise payloads, and slip away like an absolute ghost. So how exactly does it pull off this magic trick?
To figure out how this Phantom works, we're going to dissect its systems step by step, from World War II to modern stealth, the physics of invisibility, trapping radar in honeycomb cells, taming the flying wing, and finally, the smart bomb rack assembly. Okay, Section 1, from World War II to modern stealth. We really need to look back to truly appreciate the massive leap forward the B-2 represents. In World War II, U.S. daylight bombing was basically about absolute brute force. They'd send hundreds of slow, tightly packed B-17s bristling with 50 caliber machine guns, requiring whole fleets of bombers and hundreds of escort fighters just to destroy one single bridge or factory. Compare that to the B-2 stealth philosophy. The B-2 flies solo. It relies entirely on invisibility and pinpoint precision to literally kick the door down without anyone even knowing it was there. Tracking the timeline of this evolution is just fascinating. We start way back in the 1910s with World War I, where pilots were literally tossing bombs out of their laps. Then you move to the 1940s with those massive B-17 formations. In the 50s, the strategy shifted to flying way above the radar with high-altitude B-52s. But eventually, Soviet missiles made that way too dangerous. By the 1970s, we see the first real steps into true stealth, with the flat, jagged edges of the F-117. And finally, all of those hard-learned lessons culminated in 1993, when the completely smooth, invisible B-2 Spirit officially entered service. Moving on to Section 2, the physics of invisibility. So the crucial point here is understanding radar cross-section, or RCS. Radar works by sending out radio waves that bounce off an object and return to the receiver. The larger an aircraft's RCS, the further away it can be detected, right? Defensive radar networks use multiple, overlapping zones to create this massive wall of detection in the sky. But because the B-2 has an unbelievably small RCS, it can only be detected at extremely close range. This means those overlapping enemy radar networks develop giant holes that the bomber can just slip right through without tripping a single alarm. But how do you actually shrink an RCS to near zero? Well, radar behaves a lot like light. A sphere has an infinite number of perpendicular surfaces, meaning no matter what angle radar hits it from, some energy is going to bounce straight back. It's highly visible. Now, a flat plane will deflect radar perfectly safely away, unless the radar hits it dead on at exactly 90 degrees. But as you know, flat planes are terrible for aerodynamics. Airplanes shouldn't look like boxes. The real genius here is the continuous curve. Thanks to an obscure paper by a Soviet physicist named Pyotr Yefimov, American engineers figured out how to perfectly compromise between the two. The B-2 shape is this continuous, sweeping curve that provides sleek aerodynamic lift while ensuring radar waves are deflected safely away from their source from absolutely any angle. Which brings us to Section 3, trapping radar in honeycomb cells. Deflecting radar is only half the battle, right? You also have to absorb it. There's this brilliant engineering concept that says if radar-absorbent material is a sponge, radar-absorbent structures are a vacuum. I just love that because it perfectly captures the genius of the B-2 skin. It's not just coated in something special. The physical structure of the aircraft itself is designed to literally swallow radar energy whole. Right beneath the surface of the B-2 sit these hollow honeycomb structures with their open sides facing outward. Over this sits a layer of aerodynamic radar-absorbent material, a RAM. When a radar wave hits the plane, instead of bouncing off, it transmits directly through the RAM and right into those hollow honeycomb cells. The wave then just frantically bounces around inside the cell. And because the inside is coated with lossy materials containing free electrons, every single bounce converts some of that radar energy into heat. It's totally trapped. And what's wild is that this process actually generates moisture inside the structure. So to maintain integrity, the B-2 has tiny weep holes that allow the aircraft to literally sweat out the built-up moisture. It is basically a living, breathing machine that eats radar. Section 4, taming the flying wing. Defeating radar is one thing, but keeping a plane shaped like this in the sky is an entirely different battle. Here's a massive question. How do you steer a plane that doesn't have a tail? If you look at any traditional bomber, it has a massive tail fin acting as a vertical stabilizer, but to radar, a giant tail acts like a glowing billboard. So the designers simply removed it completely.
A traditional aircraft has a bulky fuselage that creates massive drag, and a tail that provides a lever for stability. The B-2, however, is a pure flying wing. The entire volume of the aircraft is contained within the wing itself. This practically eliminates fuselage drag and creates unbelievable lift. The problem? Without a tail, a flying wing is inherently prone to yaw, meaning it desperately wants to fishtail uncontrollably left and right. Honestly, without computers, it would be downright impossible for a human to fly. This is where the absolute magic of the fly-by-wire system comes in. As the pilot inputs commands, thousands of sensors constantly read the static and aerodynamic pressures hitting the airframe. Instantly, the onboard flight control computers take all this data and calculate exactly what needs to happen to keep the plane from spinning out. The computers then signal hydraulic actuators to constantly adjust complex control flaps on the rear of the wing, called elevons and rudders, faster than humanly possible. The computer is essentially acting as a virtual invisible tail. It tames this highly unstable flying wing so perfectly that pilots say this massive bomber handles more like a nimble sports car than a heavy bus.
Finally, Section 5, the Smart Bomb Rack Assembly.
We've mastered invisibility in flight. Now let's explore the muscle of the B-2 and its precision strikes. 80. Just let that massive number sink in for a second. That is the number of individual 500-pound Joint Direct Attack Munitions, or JDMs, that the B-2 can carry utilizing its new Smart Bomb Rack assembly. Previously, missions might have required 5 separate B-2 flights. Now, a single aircraft can carry an overwhelming 80 smart bombs, engaging 80 entirely different targets simultaneously.
The precision of these weapons is absolutely staggering. The JDAM relies primarily on satellite GPS, allowing it to glide directly to the target from nearly 8 miles away. But if GPS fails or gets jammed, it seamlessly switches to an inertial guidance backup system, which is actually the same incredibly accurate technology used by submarines to navigate underwater. And the rotary launch assembly holding these bombs is just a marvel in itself. It connects directly to the B-2's onboard computers. A B-2 flight might take 40 hours, right? In that time, targets move and weather shifts. The rotary assembly actually links the bombs to the bomber's computers, allowing these smart bombs to be completely reprogrammed midair to account for real-time changes. It drops the requested bomb exactly where it needs to be with minimal collateral damage. So if one single invisible aircraft, guided by continuous curves, literally sweating out radar energy, stabilized by supercomputers, and dropping dozens of reprogrammable smart bombs, can do the work that used to require 1,000 World War II bombers, what does the future of air combat actually look like? The B-2 Spirit changed the skies forever by mastering the intersection of total invisibility and absolute precision. It really leaves us to wonder, what incredible invisible marvels are engineers dreaming up next? Thank you so much for exploring the anatomy of a Phantom with me today. Keep asking questions and keep learning.